All right, everyone, we're going to get started. So I just wanted to start off by saying welcome, good morning. We're happy that you're here. Welcome to DigiCon20. We have several methods of communication for those of you with questions on logistics or if you have questions for our speaker. Please join our ESFW Global Slack channel, and there are details on that in the program that was sent to you and on our website. The Slack channel is hashtag DigiCon2020. You can also text any questions you have to 585-310-2461. Again, that's also in the program and on the website, and I can also add that to the Zoom chat in case anyone's looking for that. Additionally, you can also ask questions in the Zoom chat. So we have volunteers who will be answering your questions, and we will also be adding all of your questions for our speaker at the end of her presentation. You can also So now I would like to introduce Priya Donti. Priya is a PhD student at Carnegie Mellon, and she's studying computer science and public policy. Her research focuses on the intersection of machine learning, electric power systems, and climate change mitigation. And today she'll be talking about utilizing machine learning to address climate change. So take it away, Priya, anytime you're ready.
Hey everyone, good morning, and thanks so much for waking up this early on a Saturday to hear this talk. So as Alyssa mentioned, my name is Priya Donti, and today I'll be telling you a little bit about climate change, a little bit about machine learning, and then a bit about how machine learning can help facilitate strategies to help tackle climate change. So first, I wanted to talk a little bit about my relationship with ESW. So my ESW journey started in 2011 when I was a freshman at Harvey Mudd College. So this is our club, my junior year. And we did a lot of cool things as a club. We ran an energy competition at Harvey Mudd to try to get everyone to reduce their energy usage. And then that expanded to a 5-college consortium energy competition. So there's some pictures here of a power-free improv show that was done during that week, as well as my co-president Jake and I holding the trophy that we got for our college actually winning the 5-college competition. We also had the privilege of hosting the Southern California Regional Conference in 2014. And so there's a picture of folks from a bunch of different chapters there, as well as from ESWHQ. And there are a lot of really other good memories associated with my time as an ESW student, going to the national conference in San Diego, helping our college set up a green fund in order to fund energy efficiency projects on campus and such. And after that really great experience, I decided that I wanted more of ESW after being a student. And so in 2016, after a break for a fellowship, I joined the ESW HQ. And so there's a picture here of us using Zoom well before the world started using Zoom to do one of our meetings. And so the faces there are a lot of, for those who are students in ESW chapters, a lot of your friendly chapter relations coordinators are in there. And so I want to say for the folks in the audience that, ESW is a really awesome network and a really awesome way to have students get involved in sustainability projects and to meet other people and to sort of build a cohort and a community that is all working together to address our greatest sustainability challenges. So if you're a student, I would definitely encourage you to take advantage of this day to really meet people from other chapters and in this network to kind of grow your community. And if you're not a student, if you're a professional, volunteering for ESW HQ or being a professional member and otherwise meeting other people and mentoring chapters is a really great way to contribute to this community. So I just wanted to make that little pitch before kind of diving into the content of this talk. All right, so to get started here, what is climate change? This is a thing that is probably familiar to many of you, but I'm just going to go through a quick review so we're all on the same page. So when we talk about climate change, we often talk about the distinction between climate and weather. So weather refers to short-term variations of the atmosphere on a period of minutes to days. And this is things like, it's raining today, it's sunny next week, etc. Climate, on the other hand, refers to average weather over a longer period of time. And depending on the particular body that's studying this problem, this period of time may vary, but something like 30 years is generally what we would think about when we think about climate. And climate change then is, of course, a change in climate over time. And in today's world, we often think about a warming in the global average temperature over time. So the way climate change is actually caused is via the greenhouse effect. So let me see if I can get this highlighter to work here. Is that what I want? Anyway, so what we have is sunlight comes into the atmosphere, and a couple of things can happen to it. It can get reflected by clouds, for example. It can get absorbed by the atmosphere, or it can kind of pass through all the way down to the Earth's surface. When the sun is absorbed, or when solar energy is absorbed by the Earth's surface, a couple of things can happen. But the biggest thing that happens is that it gets radiated back out as heat. This heat can either be trapped by greenhouse gases, things like carbon dioxide, methane, water vapor, that are transparent to light, which is why they let the light in, but do trap heat, or some of it can pass through. And the basic idea of climate change, as we experience it now, of global warming in particular, is that because the greenhouse gases are trapping a sufficient amount of heat, we're actually overall letting less heat back out into the atmosphere than we're getting in as solar energy. And so since we are gaining energy, we're letting in more solar energy than we're letting out heat energy, the Earth overall warms. And this is an issue for a lot of reasons. So the human influence on the climate system is clear and growing. This is a statement from the Intergovernmental Panel on Climate Change, which is a body that kind of studies climate change, its sources, and its effects. And this is a challenge. This is a real issue because climate change has really serious consequences. We see an increased incidence of storms, droughts, fires, flooding, and some of these things are irreversible due to quote unquote climate feedback. So for instance, as the Earth warms, we might get permafrost, kind of frozen soil that melts and then reduces methane that was trapped underneath. And even if we bring the global temperature back down, we can't really re-trap that methane that was released when the permafrost melted. So there are a lot of these kind of feedback loops and cycles that occur after we reach a certain point of climate change. And so in order to avoid a certain amount of climate change, in order to avoid a certain amount of damage, the kind of statement is that we need net zero greenhouse gas emissions within 30 years, is what a lot of estimates say here. And there are a couple of reasons that fighting climate change can be a little bit dizzying. And one of them is that greenhouse gas emissions really come from a lot of different sources. So this is a chart from the World Resources Institute. And you can see that it breaks down the sources of greenhouse gas emissions by sector. So for instance, the transportation sector produces about 16% of greenhouse gas emissions globally, electricity and heat about 30%, and so on and so forth. And so there are a lot of different sources of greenhouse gas emissions. And on one hand, while this can be really intimidating, on the other hand, this can actually be kind of empowering for somebody who wants to help tackle the issue, which is that if there's something there are just many ways to kind of plug in and many ways to have an impact here. And so you're interested in tackling climate change, in some sense, you can pick a sector and really dive into the solutions in there that are likely to help reduce greenhouse gas emissions. So there are a couple of different approaches to tackling climate change, namely two that come up quite a bit. So one of them is mitigation, reducing the amount of greenhouse gas emissions we put into the atmosphere in the first place. And that, of course, reduces the extent to which we experience a changing climate in the first place. The second is adaptation. So given that we are going to experience some amount of climate change and some amount of global warming, how do we as a society make sure that we're resilient to the consequences of that, able to cope with, for example, storms and drought? And one important takeaway in seeing these two methods is that climate change isn't an on and off switch. In some sense, we can mitigate greenhouse gas emissions, but there isn't a point at which we're 100% doomed. We can always do adaptation measures in order to kind of deal with the consequences of climate change that we are going to end up having to deal with. But adaptation is really expensive. It's really uncertain. And so we really have to act fast in order to make sure that we don't have to take drastic measures later on in order to kind of adapt to climate change. So that's my brief whirlwind tour on climate change itself. And so the kind of next little, the next little portion here is I want to tell you a little bit about what machine learning is. And as you can probably guess, I will later on tell you how these two things are related. So machine learning is, something you hear about in the media. It's a branch of artificial intelligence, which is another term that comes up a lot in the media. And sometimes it can have a lot of mystique behind it, or, people are really curious as to what exactly it's doing or can regard it as even magic. But fundamentally, machine learning is actually really simple conceptually. It refers to a group of techniques that look at data, often large amounts of data, and try to find the patterns in it in an automated way. And that's really it. There are a lot of details. There are a lot of, different kinds of methods that come up here, but fundamentally you're just trying to find patterns in data. And there are a couple of terms that come up here quite often that I just wanted to really briefly talk about so that you're familiar with them when you hear them in the future. So one of these terms is deep learning. And so deep learning is a group of techniques that tries to, again, extract patterns in data, but the specific methods they use to do this are inspired by the neural networks in our brains. Very loosely inspired, I will argue. Another group of techniques is called reinforcement learning. And what reinforcement learning does is it tries to optimize the actions of some agent in some kind of environment. So agent and environment are actually really broad terms. So you can think about things like trying to optimize how a robot, an agent, navigates through a maze, an environment. But you can also think about things like trying to optimize how a battery, an agent, is charging on an electric grid, which is the environment, given information about, for instance, whether solar power is being produced at a given time, what the energy prices are at a given time, and so forth. And so reinforcement learning really tries to deal with these issues where you are trying to kind of optimize the action of some kind of agent in an environment. Computer vision is another kind of area for which machine learning and deep learning techniques are often used. And computer vision is just this idea of gathering insights from image and videos. So things like trying to figure out whether a particular image is a dog or a cat, or things like looking at satellite imagery and trying to figure out how many buildings are in a particular area, which is actually something I'll come back to. And then a final one you might have heard of is natural language processing. So natural language processing is another area that uses many techniques, but often machine learning now as well. And this is the idea of trying to understand human language, either written or spoken. So when, for example, you're having a conversation with Siri, that is using natural language processing techniques under the hood. So machine learning, like I said, is a pattern extractor, looking at data and trying to figure out patterns. And like any tool, machine learning has its strengths and it has its limitations. So some of the strengths of machine learning are that it can really scale human insight by analyzing patterns in really large amounts of data. So imagine that Alyssa gave me a bunch of images and tried to ask me, hey, can you tell me whether any of these images which of these images are dogs and which of these images are cats? I could do that. If Alyssa gave me 10 images, I'd be like, why are you asking me to do this? But sure, this image is a dog, this image is a cat. If Alyssa gave me 100 images, I'd be like, okay, this is starting to get like a lot, but sure, I will go through and tell you which ones are dogs and which ones are cats. And if Alyssa gave me 1,000,000 images, I'd be like, no, I really do not want to sit here and tell you which is a dog and which is a cat. And so machine learning can really help scale up some of the things that I can do, like identify whether an image is a dog or a cat, but do it on large amounts of data beyond basically what one or a couple of humans could do in a reasonable amount of time. Machine learning is also good at optimizing complex systems. So if you're trying to, for example, optimize how good packages are delivered through Amazon or UPS, there are a lot of moving parts there. There are a lot of trucks. There are a lot of goods. You have to figure out where the goods are coming from. You have to figure out if there are going to be delays in delivery, when worker shifts are, etc. And so machine learning is really good at sort of processing that large amount of information and using it to actually optimize the system. Machine learning can also be used to generate kind of quote unquote new data from quote unquote old data. So it can help kind of generate patterns or analyze patterns in data in a way that makes it usable to humans. So for instance, if we have, let's say, a ton of satellite data, maybe if you're a transportation network planner, what you really want to understand is where are all the transportation networks? Where are the freight trucks? Where are the trains? And so machine learning can help use satellite imagery, for example, to generate data about where the transportation networks are and where the trains are and so on and so forth. And so we can basically generate a data set of the transportation networks from a previously very large data set that it would have been hard to actually use for transportation planning, which is a satellite imagery. So this idea of generating new kinds of data from old kinds of data is something that machine learning can help us with too. And then finally, recently, machine learning has started to be pretty good at integrating with other kinds of methods. So for instance, if you are trying to do something like optimize a power grid, you have some knowledge of the physics of that power grid, but you also have a lot of data that is coming in through sensors. And so in some sense, you want to be able to use the knowledge you have about how electricity grids work, but you also want to be able to take into account the data that you're getting in to maybe correct that knowledge. For instance, if you're if your knowledge of maybe the physics of a particular part of the system is a little bit off, then the data can help tell you that. And so recently there has been a lot of work in trying to basically integrate machine learning with physics and with other domain knowledge and other techniques so that you can take advantage both of the knowledge you already have and of the data that you're getting in. So these are a couple of the things that machine learning is good at. But there are a lot of ways in which machine learning is limited as well. So one of these limitations is a pretty common term, which is referred to as garbage in, or a pretty common phrase, which is garbage in, garbage out. So the basic idea here is that machine learning is only as good as the data that you give it. So if you have, for instance, really, really limited data from really, really noisy sensors, then the decisions that your machine learning algorithm is going to make are going to be really, really limited and really, really noisy. And so in some sense, you want to make sure that the data you're giving a machine learning algorithm to analyze patterns in is actually of high quality. Even if the data you give your machine learning algorithm is clean in some sense, all of the entries look nice, you have information about every single hour in which you want to predict electricity demand. Data isn't always unbiased. The ways in which we collect data can be limited by, for example, where we have sensors or who we choose to collect it about, or the kinds of things we choose to collect or ask in the first place when we're collecting that data. And so machine learning isn't objective in any way. It inherits the biases in this data. If you give a data with biases in it, it probably will find those and replicate those. And likewise, if you try to use your machine learning model within a system that is ultimately, carrying out a biased function, then the machine learning algorithm isn't going to fix that. So I think really machine learning should be thought of as a tool and not something that sort of fixes other societal issues in data, in design, and in use. But yeah, is instead kind of a tool within these things. Machine learning kind of assumes that patterns are persistent. So what this means is that if you give a machine learning algorithm a set of data to analyze, and then you try to use that machine learning algorithm somewhere else, where, for instance, the situation has changed, the machine learning algorithm doesn't know that the situation has changed. It's just going to try to make predictions based on the data it used to have. So in one way to think of this is like, you can't teach an old dog new tricks. This phrase about, somebody who has learned information kind of in one context as the world changes may not be able to apply those same behaviors and patterns to the new context. Or if you're trying to, for example, analyze electricity usage and you have data from before a lot of self-isolation measures started taking place, you may not be able to use that analysis directly to analyze energy usage after self-isolation measures have been taken place. So lots of things like that, where machine learning has to sort of be given data that's representative of the situation it's actually being used in. There are some new methods that are starting to deal with this and trying to figure out how do you use information from, for example, from an old situation and use that to at least partially give insights about a new situation. But in any case, generally speaking, machine learning will assume that the patterns it sees in the data are the ones that it actually should be using in the future. And then finally, you would have heard this phrase, correlation does not equal causation, probably in the context of statistics. So machine learning is actually very largely statistics. And so like statistics, it can often find correlations, but it doesn't necessarily tell you what is causing what in your data. Although again, there are some new techniques that are starting to be developed that can deal with that. All right, so that was the crash course on what machine learning is. So now the question really is, of course, I've talked about these two things. I've talked about climate change, I've talked about machine learning. Now, how are these two things relevant to each other? And there are actually a lot of different ways in which climate change and machine learning are relevant to each other. So what I'm going to talk about in this talk is how machine learning can be used to kind of facilitate applications to tackle climate change in both climate change mitigation and adaptation. But there are a lot of other kinds of relationships between these two things that I'm not actually going to touch on. So machine learning, for example, is actively being used to help make oil and gas and extraction more efficient. And this is arguably something that contributes to climate change. Then there are also very large machine learning models. For instance, in the field of natural language processing, there's a very large language model called BERT. And a lot of these models can actually use a lot of energy and produce a lot of greenhouse gas emissions when they're being used. So these are really important things to be thinking about as well. I'm not necessarily going to cover them in this talk. In this talk, I'm specifically going to focus on ways in which machine learning can help fight climate change. So recently, about a year and a half ago, a number of machine learning experts were sitting at an institution called Mila, and were basically wondering about how they could use their skills to help tackle climate change. On the other side, there were a bunch of us sitting at other institutions, including Carnegie Mellon, who work on climate change, and were saying, wow, there's like a ton of data that's starting to be available about climate change or climate change relevant areas, and we don't really know what to do with it. Machine learning is going to be a really useful technique here. And so at some point, these various groups, we all met each other at a conference called NeurIPS, and realized, we are asking these questions about what is the best way to use machine learning in the climate change area, or if I'm a machine learning person, how exactly can I get involved in tackling climate change? And so a bunch of us came together to write a paper that we thought was going to be 20 pages, but ended up being 100, about how exactly machine learning can help tackle climate change. And in that paper, we covered a bunch of areas. So before, I talked about two different ways we can conceptualize tackling climate change, one of which is mitigation, reducing greenhouse gas emissions, and one of which is adaptation, being resilient to the effects of climate change. And so in this paper, we sort of cover applications of machine learning to mitigation adaptation in various ways. So in electricity systems, transportation, buildings, farms and forests, via things like solar geoengineering. And we also cover ways in which machine learning can help contribute to frameworks that can help us then implement climate change mitigation or adaptation measures. Things like, how can machine learning help us take individual action or make collective decisions through policy or markets? And how can it contribute to areas like education and finance in a way that's beneficial to climate change? So this is if you're interested in this area, I would definitely encourage you to check out the paper or the interactive summaries that are on the website associated with the paper and a bunch of other related initiatives, and I'll get to that later. But here I'm going to go through a couple of applications that I think are particularly cool and are particularly illustrative of the different ways in which machine learning can plug in here. All right, so first application here. As we start to use more renewables on the electric grid, things like solar power and wind power and other low carbon sources of energy that vary based on the weather, this starts to be a challenge for electricity system operators. So on a power grid, you can think about the way that power needs to be managed as needing to kind of maintain this really precarious balance all the time, where on one side of the balance, you have electricity supply, things like solar and wind power or natural gas and coal power that's being put into the electric grid. And on the other side, power that's being taken out of the electric grid as you and I, for example, use the internet or use lights or use heating and cooling systems. We draw electricity from the grid, generally speaking. And the amount of power being put into the grid and the amount of power coming out of the grid have to actually balance each other out at any given time. And so you can imagine this becomes really difficult when you have things like solar power and wind power, where you can't predict exactly how much is going to be produced ahead of time, or where you have humans with free will, where I can decide to turn on and off a light next to me at any given time. So what machine learning can help do is actually help forecast both supply and demand in the short and medium terms in order to basically give electricity system operators who are trying to balance these systems some foresight to predict what is going to happen in a few hours or a few days so that they can adjust equipment on the electric grid accordingly. And so historically, machine learning has been used here a lot, using things like historical data in order to predict demand today. Maybe I would want to know demand yesterday. Using the outputs of physical models, there are things like numerical weather prediction models, which are physical models that try to predict how much sunlight's going to be in a particular area. And also things like image and video data. So there have started to be these applications where you'll have a solar panel and you'll have a camera next to it that's pointed upwards at the sky. And this camera is basically getting images of where the clouds are. And so based on that data, you can kind of predict, well, is a cloud going to come over my solar panel at this particular time and therefore shade it? And there are a lot of basically important considerations that have started to come into play when using machine learning algorithms in these areas. So one of which is, how do you make sure these machine learning algorithms are incorporating the physics that we know, for example, about how weather works, or the goals of our system? Does our machine learning algorithm know that an electricity system operator is going to use it to balance supply and demand? And then a lot of machine learning algorithms have started to do things like characterize uncertainty. Say, for instance, if I'm very confident that I'm going to get a certain amount of solar power tomorrow, then that should inform an electricity system operator's decision differently than if we're not very certain about that particular forecast. And then relatedly, the area of interpretable forecast is one that's really starting to burgeon within machine learning. The idea that if I create a forecast as a machine learning algorithm, that I can tell you why exactly that forecast was created and what kinds of factors influenced it. So this area of forecasting is kind of the first thing that a lot of people think about when they think about machine learning. And indeed, it does come up in a lot of areas of climate change, and I'll kind of get back to that later. So a different kind of problem that machine learning can help us address within climate change is one of gathering data. So I mentioned earlier that one of the strengths of machine learning is that it can help us take data that we can't necessarily use in certain applications and transform it into data that we can potentially use in these applications. And so in particular, in a lot of climate change, in decision-making scenarios, or when you're trying to make a policy, or when you're trying to simulate something, or when you're trying to build a system, there's a lot of data that we don't actually have that would be really very useful to have. Things like, how many buildings are there in the world? If you actually try to Google this, there isn't really an estimate anywhere. So how many buildings are there in the world? How efficient are these buildings? And as a result, what energy efficiency measures should we be taking in different areas? How many freight trucks are there in the world? And as a result, how much freight is being transported on the road as opposed to, for example, being transported in trains? These are a lot of questions that we don't necessarily have great answers to. And so machine learning can basically help use satellite imagery or other sorts of data, like satellite imagery, aerial imagery from planes, drone imagery, etc., to actually try to analyze some of these questions, to try to analyze buildings and electricity infrastructure and the like, in order to then be an input to other things we may want to do. Another strength of machine learning I talked about earlier is optimizing systems, the ability to take into account a lot of different information in real time and then make decisions on that, based on that. And so one application where this is particularly useful in climate change is the concept of freight routing and consolidation. So when we think about transportation, often many of us think about passenger transportation. So how do I get from place to place, for instance. But 50% of emissions from transportation do come from freight, from the movement of goods across the world. And freight is moved in really complicated freight transportation networks where you have, trucks and trains and suppliers of these goods and users of these goods, and these all have to be optimized within the same system. And so within this system, we would actually really like to reduce the emissions that freight is actually producing. So machine learning can come in here by helping to bundle and optimize shipments. So for instance, if you have, a lot of different trucks that are trying to coordinate with each other to hand off goods, then you can try to use machine learning to predict when are they going to arrive, when are things going to be disrupted, and as a result, which shipments can be bundled together. And machine learning can also be used to cluster suppliers. So what this means is that if you have a bunch of different entities that are producing things and shipping them to the same places, then you can use machine learning to identify, oh, wow, these particular suppliers should actually be coordinating together to pack the things that they're producing into the same trucks in a way that reduces the amount of trucks that we need in the first place. So machine learning can kind of help optimize this really complex network of freight transportation in a way that ideally will reduce emissions. Yeah. And they're called this. All right. So when we think about climate change, we often think about, electricity, renewables, renewable transportation, or more efficient buildings. But one thing we don't often think about is agriculture. And agriculture also contributes to, I forget the exact figure, but I think around 12% of global greenhouse gas emissions. And so it's something that we really want to think about. And agriculture kind of produces emissions in a couple of different ways. So when you kind of grow one kind of crop, monoculture, on a very large patch of land, maybe you're exhausting the soil on that particular land, and as a result, you're having to use fertilizer. Fertilizer takes a lot of emissions to produce. When you actually till the soil and displace the soil, you are actually disrupting some of the organisms in that soil that are actually sequestering carbon dioxide. And so that can have an effect on greenhouse gas emissions. And so there are a lot of different ways in which agriculture does contribute to producing greenhouse gas emissions. And so there's a real need to reduce emissions from this area. So one way machine learning can help here is by bringing automation into agriculture in a way that allows farmers to work with the land in a way that is more beneficial to the land, and as a result doesn't exhaust the soil as much or doesn't displace organisms as much, and as a result kind of avoids excessive fertilizer use and soil displacement. And so, for instance, while in order to manage a large farm today, you would have to think about, okay, we want to plant only corn on this field, and that way we can treat all the plants the same, we can spray them all the same, etc. You could think about instead saying, well, maybe if we grow on this field a mix of corn and wheat and carrots and other crops, then that might be healthier. But then the question is, how exactly do I do this at scale? How do I kind of make sure that the carrots get the treatment the carrots need and the wheat gets the treatment the wheat needs, and so on and so forth? And so, like I said, machine learning is really good at scaling things that humans can do. And so this is kind of a really ripe area where machine learning can help. So one of these areas is robotic farming. There are a lot of robots that are being developed today that can basically navigate through fields of crops and try to, for example, use cameras to identify, well, is this particular plant healthy? Is it damaged? Does it need treatment? And so these and then actually apply the treatment. And so kind of robotic farming techniques can help enable this kind of heterogeneous crop field kind of concept. And then another one is intelligent irrigation. Again, being able to sort of intelligently manage based on the health of the crops in a field when those crops need to be watered and when those crops don't need to be. And so this is another application where basically machine learning can be taking in a lot of information from sensors that are in the field, from robots that are navigating through the field in order to help make some of these actions a little more scalable. So the various applications I talked about so far have been in the area of climate change mitigation, so trying to reduce greenhouse gas emissions. But there are a bunch of areas of climate change that try to understand what's going on in the climate or to adapt to the effects of climate change, as I mentioned earlier. And so in particular, we actually have a lot of climate models that are often run to try to understand what exactly is going on in the climate, and as a result, how we can actually adapt to that. And a lot of these climate models are really computationally intensive. It takes a really long time to run them, and we can't necessarily run them at a really like spatially granular scale. So if a particular city wants to know exactly what's going to happen to them because of climate change, we often can't generate that answer, because generating this answer for every single city would actually just take up way too much computational power. And so machine learning can help actually reduce the complexity of some of these simulations or portions of these simulations. So one of the hardest things to measure in climate models is clouds, because sometimes clouds can kind of reflect sunlight and push it back out into the atmosphere. And sometimes clouds are like a warm blanket over the earth that actually, you know, trap heat and as a result warm the atmosphere. And so getting models of clouds correct can be really important, but can be really computationally intensive to actually put into a climate model. And so there have been some uses of machine learning to actually take our cloud models and to actually approximate these cloud models in a really efficient way. Another kind of issue that can come up in climate modeling is that sometimes we don't always have accurate data to put into the climate model, and as a result that affects the accuracy of the simulation. And so using some similar kinds of techniques that I was talking about before when I was talking about satellite imagery, there have been a lot of uses of satellite data to actually gather information about ice sheets and sea level rise and other phenomena that we would want to stick into a climate model. And then the last kind of area application that I'm going to talk about is this idea of societal adaptation. So sort of given that we, you know, have tried our best to mitigate greenhouse gas emissions, which we should absolutely be doing, and given that maybe we understand the extent to which warming is going to occur using our climate models, now what do we actually do as a society to adapt? And there are a lot of different applications here, which I'm going to just give you a second to look at the slide and sort of see that there are many, many applications. But a lot of these basically have to do with things like trying to monitor ecosystems, trying to make our infrastructure more resilient, and try to make us more resilient to crises that may happen by doing things like forecasting when floods will occur. So those were a couple of applications that come up through the paper. And of course, there are many, many more, as you'd expect when the paper is 100 pages. But there are a couple of kind of recurring themes, recurring ways in which machine learning can contribute here that tend to come up over and over again. So one of them is forecasting. So I talked about things like solar power, but maybe you also want to forecast when a hurricane is going to happen, or maybe you want to forecast if you have a carbon market, what the prices in that market are going to be. So forecasting is something that comes up quite a bit. Another application that comes up is basically when we are experiencing maybe like a real-time crisis, or we want data in order to make a decision, trying to basically get that data somehow. So there are a lot of applications of an area called data mining, or which machine learning is used for example, to, during a disaster, figure out using Twitter where people are, whether people are safe, etc. Remote sensing, which is related to this, so the idea of using satellite imagery or aerial imagery, etc., to get information about emissions or infrastructure data, or stuff I didn't talk about, like deforestation. Where is deforestation happening, and as a result, can we stop that from happening? It can help approximate simulations that take a lot of time and compute to run. So I talked about climate models, but this comes up with electricity system models as well. And then an area I didn't talk about is accelerated experimentation. So as we try to discover new batteries or new solar panel materials, or we try to make nuclear fusion work, there are lots of ways in which machine learning can kind of help plug in there. And to be clear, these areas are going to require, you know, fundamental science and engineering, but machine learning can help, for instance, help scientists figure out if I'm going to synthesize a material in a lab and I can only synthesize 5 materials, which of these materials should I actually try to synthesize in order to increase the chance of success that these materials will actually be good for solar panels or be good for next generation batteries? So there are a lot of applications like that in an area of machine learning called Bayesian optimization. Machine learning can help optimize systems or control systems. So I talked about precision agriculture, but also machine learning can do things like control how high or low your thermostat should be set in order to optimize for the comfort of people in a building, but also to try to reduce the amount of energy used. And then, so a lot of these application areas that I've talked about are often kind of, quite sexy as applications. People are like, oh, awesome, I get to use machine learning to, help contribute to nuclear, or to help facilitate the discovery of nuclear fusion, etc. But a lot of machine learning applications in climate change, and honestly, a lot of work in climate change is kind of unsexy. And so predictive maintenance is another, is an example of this, where, for instance, if you have a power grid or you have natural gas pipelines that may leak, natural gas is natural gas is the same thing as methane, which is a really, really potent greenhouse gas. And so if you want to figure out, is my pipeline going to break? Is there going to be a leak? Machine learning can help do this in an automated way, which is very useful to the climate, but it is not necessarily, a very sexy application, but is very important. All right, so these are a couple of the recurring themes that come up throughout the paper. And I hope that sort of through the last few applications, you kind of have seen that machine learning can plug in a lot of different ways to help facilitating the fight against climate change. But one thing I do want to emphasize is that machine learning is only one piece of the puzzle. So it is a really, really powerful tool, but it's not a silver bullet. Tackling climate change is going to require approaches from classical engineering, from policy making, and from a lot of different areas. And machine learning can help sort of plug into these different techniques or even accelerate some of these techniques, but it's not going to be the thing that solves the problem. Having a career in machine learning is not going to be the thing that helps you fight climate change. Really, like, a lot of different techniques are needed. And in particular, because a lot of problems in climate change do require expertise from many different areas and many different kinds of people, collaboration is really important to doing meaningful work. All right, so final portion of the talk, which is, what does this mean in practice? So I've, again, hopefully convinced you that there are lots of ways in which climate change and machine learning are related. But what does this mean for you as potentially a practice engineer, or somebody who maybe does or doesn't know a ton about machine learning ahead of time? So one thing you can do is actually use some of the data sets that are generated by machine learning methods. For instance, there are data sets like Deep Solar, which was produced using machine learning at Stanford, that tries to basically quantify where the rooftop solar panels are across the United States, because this is something that we don't often have data on. So just using data sets generated by machine learning methods and being aware about the ways in which they might be limited, this was the strengths and limitations slide I talked about before, is a great way to leverage machine learning methods. Another way is to engage with machine learning experts. So if you're working on a problem, for instance, where you know that now that you have a bit of a mental model for what machine learning can do, if you're working on a problem where you're like, maybe machine learning can help us solve this particular sticking point we're having here, then maybe you want to kind of engage with or talk to machine learning experts. And there are a couple of ways to do this. If you are at a university or you're at a company, there are a lot of kind of implementation and research projects that are going on that often want to bring in experts from different areas. A lot of machine learning people, for instance, are working on climate change topics, but would really like to be engaging with people who know more about maybe the engineering of the electricity sector, or civil engineers if they're working on a transportation area, in order to be able to develop better applications and better solutions. So just collaborating with people is one way to do this. Or if you're working on a project where you just really need to bring a machine learning person in, a lot of companies have started doing pro bono, a lot of data science companies have started doing pro bono consulting. So you can, for instance, get some of these consulting companies in, or you can even kind of, hire or bring in machine learning experts in-house, quote unquote, where appropriate. And then finally, you can get hands-on. Machine learning and statistics are really kind of easy to access these days, because there are, a lot of free machine learning and statistics courses and resources. And if you're at a university, taking statistics classes and machine learning classes can be a really great way to get insight into this area. There are a lot of open source libraries and out-of-the-box models that are online. So for instance, if you want to detect objects in satellite imagery, there are a lot of out-of-the-box object detection models that you can just use that are already online. And then you can engage with people who are actively thinking about this area, who are thinking about machine learning, who are thinking about climate change. And one of these communities is one of the ones that I run, called Climate Change AI, which I can tell you a little bit about now. So Climate Change AI is an initiative to facilitate meaningful work at the intersection of climate change and machine learning. And we do this by sharing knowledge and resources, and by holding kind of events, both physical and digital, to try to bring people together to discuss topics in this area. We're also the group that wrote that 100-page paper, which is on our website here, along with sort of summaries of the paper. But also we have like a newsletter and a forum that you can plug into that are really cool. So this is the team. The team includes people from a lot of different institutions, and both from the machine learning and computer science side and from the climate change side, which we think is really, really important. Like I said earlier, collaboration is really key to making sure that we are deploying meaningful solutions and actually tackling meaningful problems. So if you are in the mood to attend additional digital conferences in addition to this one, we actually will be running a digital conference from April 26th to the 30th. More information is available on our website, but there'll be kind of different days during this conference that are focused on climate change and machine learning as a whole, but also a day for energy, a day for agriculture, forestry, and other land use, a day for climate science and adaptation, and a day focused on cross-cutting methods in machine learning. So if you're particularly interested in any of these areas and want to kind of stop in, the live stream for the main workshop day will be free on our website. And if you want to sort of interact with and meet other workshop participants, then there's a registration fee, and more information is on the website. As I mentioned, we have a digital discussion forum, which is also really cool to participate in. You can basically go on there to, ask questions about climate change and machine learning, or if you have a project that you're working on that you think might be useful to get some feedback from the machine learning community on, or from the climate change community on, then you can do that here. There are also a bunch of job postings that are available here and also on the Climate Change AI newsletter. So with that, thank you so much for, again, starting the morning with me here, and I look forward to your questions.
Awesome. Thank you so much, Priya. What a great presentation. We do have a few questions. If anyone else has additional questions, like I said, you can text that number, you can add them to the ESW Global Slack, or you can put them in the Zoom chat. To start off, especially with using machine learning techniques in a relatively quickly changing electricity field, how do we make sure we are incorporating the changing generation mix?
Yeah, that's a really good question. And so when we want to make decisions, we often think about like the horizon in which we make them. So sometimes electricity system operators want to know what's happening, a minute from now, or 5 minutes from now, or days from now, years from now. And so the question here is, what data are you using to make a decision when? If I'm trying to forecast electricity, if I'm trying to forecast power generation tomorrow, and I use data from today and the last few days and the last few weeks, the electricity generation mix is obviously going to look pretty similar tomorrow as it did in the last few weeks. And so in that sense, you can kind of use the latest data in order to make short-term decisions. As you start to make long-term decisions, so as you start to make decisions about, well, in the medium and to long term, like, should I build this power plant? Where should I build this power plant? And so on and so forth. That's a lot harder to do if you're just using data from the last few weeks, because as the person who's asking the question is rightly saying, the generation mix is going to change. And so that's where you want to use a combination of data and models from other areas. So for instance, there are electricity planning models that exist. There are other sources or ways that we can think about figuring out what the oil prices are going to be like in the future. And then you do want to take into account maybe data that you have about, for example, past oil prices, or about the way that solar panel prices have decreased. And so in a kind of a longer term, the way you want to deal with the changing generation mix is by bringing in a combination of data-driven techniques like machine learning, but also physics and other expertise in order to sort of combine these things and come up with answers for the future.
Awesome. All right, next question. If we rely on sensors and smart devices or infrastructure for data, how do we mitigate the bias that more of those sensors will likely be in more wealthy areas?
Yeah, that's a fantastic question. So there are I think, two major ways I can think of mitigating the bias around sensors being in more wealthy areas. The first has nothing to do with machine learning. The first has to do with policy. So we should make sure in some sense that this is not the case, that our political incentives and structures are set up to ensure that we are installing sensors in a more equitable way everywhere. So for instance, electricity system operators are basically entities called ISOs and RTOs. Their mandate is to kind of ensure kind of low cost energy sort of and fair competition across their entire area. And so we're building in incentives and mandates to these authorities that regulate these different areas can be a great way to ensure that it's not just, you know, a rich person paying to have a sensor near them, that there's really fundamentally in the policy structure something that's incentivizing sensors to be installed everywhere. So that's on the policy side. Now, given that we unfortunately do live in a biased world and those things are never going to pan out 100% properly, then you may ask the question of how can machine learning techniques actually deal with biased data? And there are a couple of methods, things like transfer learning, where, for instance, if you have information about only a wealthy area, you can try to start asking questions about which of these insights actually generalize to other places and which of these insights don't. And you can basically use maybe a limited amount of information you have about another area along with some of the insights that you're getting from the areas where you have a lot of sensors and combine these two things together to try to get insights. So machine learning can try to start dealing with some of these issues, but I think fundamentally the solution there lies outside machine learning, where we do need to make sure that the way the sensors are placed in the first place is equitable.
All right. How do we best communicate the knowledge learned from machine learning models of climate change acceleration, emissions, etc., so that society, policy, industry can properly use it to inform decisions?
Yes, and so I think there's a lot of temptation in the machine learning community to do one of two things. If you're a researcher, you publish a paper in a machine learning conference, and then it's only seen by machine learning people. This is not the right way to communicate things to policymakers and other audiences. Another thing that happens is that a lot of solutions are developed sort of in startup companies, where the solutions or the ways in which they're developed are proprietary, and then they're sold. And then as a result, they can only be sold to people who have the money to pay for them. And so I think that there are a couple of ways to mitigate this. One of which is people who are working in research should actively be seeking out communicators. A lot of universities actually have media offices that are really excited to hear about student work and student research and are excited to work with you to actually communicate that to the audiences you want to communicate that to. So taking advantage of some of these resources can be really important. And then another way to make sure that results are communicated to a particular audience is to actually work directly with that particular audience. I would argue that if you're developing a solution in a university that is meant for a policymaker and you never involved the policymaker in actually developing that solution, then your solution is probably not going to work. And so there's an aspect of communication which is really like in the process of creating the project, which is going back and forth on what needs to be done, how it needs to be done. And then by the end of the project, you and the policymaker, you and your audience are actually just going to be on the same page because you both had a hand in developing that particular solution. So that's another way I would say is really important.
Awesome. We've gotten 2 audience questions in. The first, would you say that machine learning for intelligent systems is more important than machine learning for data science within climate change modeling?
So I hesitate to say that machine learning for any particular application within climate change is more important than machine learning for any other particular application within climate change for a couple of reasons. So climate change is not, you know, it's not something where we're going to find one golden area that we need to be working on and that is going to solve everything. We need really like every area. This chart that I showed earlier, that I can pull up again, I think. But this chart that I showed earlier at the beginning of the presentation, talking about the various ways or various contributors to greenhouse gas emissions. Sorry, this is going to be painful to flip through, I think. Let's see. Let me reshare my screen here. All right. So this particular chart from the beginning of the presentation shows that there are just so many different sectors in which we need to tackle climate change in order to make a dent in the problem. And within each of these, there are many ways that machine learning can contribute. And so I wouldn't say that the distinction is really like, is machine learning getting data more important than machine learning in optimizing a system? That answer will vary based on the kind of data that you're trying to get or the kind of system you're trying to optimize. But the way I would try to conceptualize whether machine learning is good for a particular application is that application a big contributor to greenhouse gas emissions? And is the use of machine learning in this application going to help alleviate a bottleneck in actually addressing that, in actually pursuing that path? So for instance, in freight transportation, we actually have very little data about how freight moves. And so getting that data can be really important in kind of informing policymakers about what they should do there, possibly more than optimizing the system in that case. Whereas on an electricity system, we have a lot of data in a lot of different places, and so optimizing the system may be more important there. So I realized that was a kind of roundabout answer to that question, but the answer is it depends.
Sure, that's the best answer, right? Okay, last question we have. I liked the use of machine learning for forecasting supply and demand. Do you know of any ways of forecasting the energy consumption of the eventual user of solar systems?
Yeah, so there's a lot of work there, which is basically trying to forecast how a particular user in a particular home is going to be using electricity. And this is actually used a lot when thinking about kind of applications of, should I install a battery on this particular home? So if this home produces solar power, should that solar power be put into the grid? Or should it be kind of stored in a battery? And when should that user be using it? And so, yes, this is definitely an area people are working on. I believe there are some references in the original paper about it, but if not, feel free to check it out and email me and I can give you some more information. I guess I didn't put my email anywhere on these slides, but I have a website, priyadonti.com, and you can find it there.
Awesome. Yeah, we can also, we'll be uploading this presentation eventually to YouTube. So we can either put your email there or we can send it out in, you know, a post-conference email, you know, whatever you're more comfortable with. So yep. If people have additional questions, you know, if you want to get involved in anything that Priya's doing, or, you know, if you are interested in machine learning, you know, we can help connect you. All right, well, I think that's all the questions we have, and it's perfect timing. So thank you very much, Priya, for hopping on this morning and talking to us about machine learning. It was incredibly informative and very insightful.
Thanks, it was really great to be here, and yeah, looking forward to DigiCon.
Awesome. Well, we're going to take a brief break, but you should check out some of the content that was released on our ESW YouTube account. So we have a lot of different videos going live throughout the day on our ESW YouTube account. Some are previously recorded presentations by individuals who just want to, you know, give us content. Some are actually old ESW short courses. So hop on to our ESW YouTube account. You can find details in the program that was sent out to you and on our website. And come on back to Zoom at 10:30 for Amanda Richardson's presentation. So thanks for hopping on, everybody. We'll see you in a little bit.